Thank you for joining from wherever you are located in the world. I am Lynn Karg. I am one of the 3 chairs of Climate Change AI, and I will start us off with a small introduction to the session and to Climate Change AI. Okay. Can everyone see the screen?
Yes.
Okay, great. Welcome to the Climate Change AI webinar on machine learning for oceans. Today we are joined by Andrea Rivera Sosa from the Coral Reef Alliance and by Oliver Zielinski from the DFKI and the University of Oldenburg. I'm getting confused with German and English. I wanted to start us off by a few words about Climate Change AI. So we are an organization that is dedicated to catalyzing impactful work at the intersection of climate change and AI. And we run a global network of researchers and policymakers, entrepreneurs, and other stakeholders who are interested at this intersection. And we provide a number of different resources for working in the space. We also provide advice for relevant stakeholders. And we run events such as this one. We've also run a number of workshops at large AI conferences. We run events at the UN Climate Change Conference and so on. And you can find recordings of all of these events on our website. You can also search for all the accepted papers to our workshops on our website by keywords. So this is a rich repository of ongoing work in this space. We have a community platform that you're welcome to join if you want to exchange ideas with people who are interested in the same kinds of research at this intersection of machine learning and climate change. You can find the link on our website as well. We also have a directory where if you are working at this intersection and you want to share that publicly, you can sign up here as well. We run our own blog series that synthesizes and explains work in a shorter, more understandable way that features like different research projects, but also ideas that relate to this intersection. And we have a community-driven wiki that is a living repository of work at this intersection. If you want to stay updated with recent events, opportunities, readings, and job offers that relate to climate change and AI, sign up for our newsletter. We send it out every month. And we also have a website where you, for example, can sign up for our happy hour or for future webinars that we run monthly. With that, I wanted to introduce our distinguished speakers of the day. The first talk will be by Oliver Zielinski, who has been professor of marine sensor systems at the Institute for Chemistry and Biology of the Marine Environment at University of Oldenburg since 2011. He's also the head of the research department Marine Perception at the German Research Center for AI. And he also leads the Competence Center AI for Environment and Sustainability. He completed a PhD in physics, and he also spent time as the CEO of an international sensor systems supplier before being appointed professor at Bremerhaven University of Applied Sciences. His research covers environmental physics of aquatic ecosystems. He's utilizing intelligent technologies, especially in the field of autonomous sensor systems and marine observatories. The second talk will be by Andrea Rivera Sosa from the Coral Reef Alliance. She is a coral reef scientist who has studied coral reefs in the Virgin Islands, Maria, the Hawaiian Islands, and the Mesoamerican region. She's also a doctoral candidate in marine science, as well as a diver, a reef monitor, and a trainer on coral bleaching, stressors, and ecology. As a project and outreach manager at the Coral Reef Alliance in the Conservation Science Program, she also works with multiple groups and scientists across the globe to monitor coral bleaching and coordinate on-the-ground responses to help validate and improve the Allen Coral Atlas bleaching detection tool. So we will now start off directly with the talk by Oliver. I will stop sharing and hand this over to you. Feel free to share your slides now.
Thank you very much. I will share my slides and I hope you can see this.
Yeah, this looks good.
Perfect. So I will put you all in the back. Okay, let's go ahead. Yeah, thank you for having me today. And it's really a pleasure to present here a bit of my work and my passion. And thank you also for introducing myself. So I'm Oliver, and my interest is indeed in between physics, marine science, and smart technology. So there was already some words about my positions that I have and the way I went in my career. But I'd like to mention here that on the one hand, I started in my first job with maritime pollution and aircraft equipment. And then I did a lot of work in also in the field and on vessels. And you will see at the end of this presentation that things often return in life. Yeah, the main or my overall objective is to create tools for stakeholders so that people can take care of their environment and that they can protect the seas, the oceans, or aquatic environments in general. And that is also the main driver for both of my groups that I'm heading. Let's start with some words on the oceans and why they matter. I mean, there is some figures, some key figures that you might know, that we have more than 50% of oxygen on Earth originates from the ocean, and 80% of all life on Earth can be found in the oceans. And also the oceans provide food to millions of people. Oceans store the heat that we generate and to 93%, and also they absorb the CO2 emitted by humankind. So there is a strong link between oceans and climate, and basically you cannot study climate change or climate mitigation without looking at the oceans. It's also relevant for humans. I mean, we are a land-based mammal, but of course the oceans, they provide food, transport, recreation, energy, and it's a fact that more than 50% of human population is close by the sea, and also most of the mega cities with more than 10 million people are located by the sea. So also humanity and oceans are closely linked in their fate. There are also, of course, risks and pressures. And from left to right, you see something like on the left hand, sea level rise, affecting our infrastructures, our cities, but also natural habitats. In the middle, there are extensive nutrients, change ecosystems. They can lead to harmful algae blooms like this red tide here in Norway. And on the right-hand side, of course, the picture that we got already used to is this littered beaches, which is really a pity. This one is in Puerto Rico, right beside the Bacardi distillery. And so when you think about Bacardi and pure beaches, maybe rethink. Let me talk briefly also about ocean science and technology. You know, marine research is closely linked to vessels. It's closely linked to expeditions on research vessels which cross the ocean. And the start of modern oceanography was the 1872 expedition by the Challenger. And from then on, we have a series of research vessel activities all across the globe. Here on top, Maria Esmerian in Greenland. And what you do on such a research vessel is that you kind of take water samples. You have this rosette with water bottles. You take your samples and you lift them up to the vessel, and then you bring the water samples to the lab, and then there's someone maybe doing taxonomy under a microscope, or you've filtered the sample and you use all the chemical or biological analysis tools that you have, or you just bring them at home. So this is traditional oceanography, and it's still a key element of any oceanographic observation, process understanding, etc. But there's more than that. Nowadays, modern oceanography is utilizing a plethora of platforms and sensors, from moorings to buoys, from vessels of opportunity to radar systems to satellite, and also autonomous underwater vehicles, gliders, floats, crawlers. There are so many platforms which are used autonomously, semi-autonomously, or just in a manual, remotely operated way. Now, let's think about AI and what AI can do in support of ocean science and technology. First, well, this is an image just released from NVIDIA when they launched their NVIDIA Earth 2 system, and they highlighted and tried to illustrate what physics AI and physics-informed AI can do in combination with a visualization tool. And it's really true that the computational power that we have nowadays, combined with the algorithmic developments, can make climate models, weather models, any forecasts or hindcast understanding much more efficient, and we can be more quicker in that way. On this global scale, there are several studies using machine learning or AI to foster understanding, process understanding, and knowledge gain. And I just picked one here from Maike Sonneveld, where they looked at biogeochemical models, global models, and they then used unsupervised learning to determine and classify marine ecoprovinces in the global ocean. Ecoprovinces which are characterized by unique or by typical combinations of, on the one hand, plankton species, and also on the other hand, nutrients. And this is very interesting to see, because when one of the foundations of global biogeochemistry is this Longhurst view graph in the upper left. Because Longhurst, he looked at all the ecological areas in the ocean and tried to sort them out and define these provinces. But you see, it's of course human-made. There are right lines drawn between areas, so everything is very distinct. And it's good to see that using unsupervised machine learning combined with ocean models, you can kind of find dynamic patches and the more look deeper into the structure of the ocean. I picked also this example from Maike Sonneveld et al. Because I can recommend here the CCI AI webinar that was given in October last year. And this webinar touched the global aspects of climate science and Earth observation. And there are two brilliant talks there. I'd like to refer you to them. And this is really the global scale where you can see what water mass and following large scale models and what physics informed modeling can do. In my presentation, I will now go to the more regional scale and also look more for how can we interlink AI with observational techniques and how can it help here to get better understanding. And I will, my first example is starting at the island of Spiekeroog, which is an island just close by my home here in north of Germany at the North Sea. It's a barrier island. And around this island, we operate an observatory with lots of sensors and parameters observed. The observatory in itself is operated since 20 years now, and we just recently published an overview on it. Thinking about such an observatory doesn't mean that all the data that you gather is available all the time. But when you look at larger timescales, you will see that you always have dropouts in the data, you have cleaning cycles, you have batteries going low, you have dropout of sensors, and you have to repair them. So you always have to deal with the data. And this brought me back in 2015, 2016, to the task of imputing data gaps. And that was a collaboration with Oliver Kramer and Stefan Oehmke. And we took these time series data and used gap imputation with KNN ensembles and a time warping metric to efficiently fill the gaps between the data, which is needed because it's a tidal regime, and if you just use linear gap filling, it wouldn't do the job. We then, in the next step, used virtual marine sensors because we had a complete dropout of one of our sensors, and this sensor was essential for the observation, but we could use the data from the past to train a combined deep learning LSTM network, and by that way substitute the missing sensor and kind of provide this essential data on the spot. In recent years, in the last 2 years, we focused more on event detection and change detection. So our task is now to find changes in the system, to see where sudden changes happen, where recurring changes happen, gradual or incremental changes, and to see when these changes, when these events happen, to sample. So changing the philosophy from regular sampling schemes to a more event-based sampling, which is more informed, more smarter, and more efficient in that way. So this is part of a project which is currently going on called CHESS. And in this CHESS project, the central architecture is this framework of data integration or data ingestion and caring, and then event detection with several methods and humans in the loop. So we already did some pre-examples and used that also in different time series. And when you're interested, I refer you here to Frederik Stahl from my group. But in the next step, we think about, we entered the world of digital twins, and digital twins are now everywhere, also in the ocean science community. There is a strong initiative launched last year by the UK in the G7 leadership to bring up a digital twin ocean. And this is part of the European strategy, Digital Twin Earth. And ESA is taking responsibility for setting up one of these digital twins and collaborates with DFKI here. And I'd like to show you one of the examples where we are involved, which is the using a digital twin or developing a digital twin for the use case of offshore wind farms and their effects on the marine ecosystem. Of course, there are several digital twins already and prediction systems for wind farms and the energy they can get and also the wind field and so on. But the fact that wind farms also have a major influence on the marine ecosystem, they disturb it, they change buoyancy, they introduce energy, is not well studied, and we try to provide here more insights with the DTE. This is a setup that is part of the overall project, and without going in all of the details, we just identified on different layers of a digital twin where AI can be of help. Our use case is here on the right-hand side, and we focused here on event detection, imputation, and the methods I showed before. So what we do is we take data from the wind farm, which is Dantisk, which is located between Germany and Denmark, and it's west of Sylt in the North Sea. It's a large wind field, and we take data from Sentinel-3 satellite, the Pheno station, which is a marine station taking weather and currents information, and we take data from the BSH hydrographic model, which is run operationally, and combining them, putting them on one grid by using KNN algorithms. Then we use data imputation in a way I showed you before. And in the last step, we looked for different anomalies. And currently we're testing different algorithms here on the temporal and on the spatial scale. You're looking for local outlier factor, one-class support vector machines, isolation forests, or copular-based outlier detector. And I'm happy to take any more advices and ideas of what methodologies one can use here. And also here the contacts are Janina and Andre on the lower left here. Let me come to my second example. A complete different story. It's out in the ocean, and you might have seen this picture before. It's originating from the Ocean Cleanup, the company or NGO which is trying to clean the oceans of the plastic debris and the litter, which you can see in the insert here. Well, one has to say that this effort is well needed, but it's also very complicated because the ocean is large and the forces are strong. So it's very difficult to clean the whole ocean, but it's easier to go up the river. I will have that in a minute, but it was the entry point for us. This exercise with Ocean Cleanup was the entry point for us. And we joined one of the campaigns with Ocean Cleanup aircraft, where they counted debris and floating litter in the Great Pacific Garbage Patch in the North Pacific. And we used spectral analysis to identify and look for the different plastic types in shortwave infrared. We transferred part of this, or this was to drone imagery and drone applications. And we were contacted by World Bank 3 years ago if we could use the technology and the knowledge in helping to quantify and classify what litter we find in rivers in Asia, and this started in Cambodia, and how we can use the technology also to provide capacity building, and so it should be easy to use and easy to apply for the stakeholders. What we did is we developed a methodology using commercial off-the-shelf drones and flight patterns, etc. And then on the data that they received, we developed a two-step CNN solution, which was supervised machine learning approach with which in the first classification step classifies if there is litter or not, which is the uppercase here, this gray areas, gray-blue areas to see where is litter or not. And then in the second step, we went to a fine grid classification to say whether we have cans, plastic bags, small bottles, bowls, or whatever, styrofoam, strings, cords, according to an international agreed list. The main result people were interested in were top 10 items here. So it is relevant for them to know what are the top 10 items, where can policymakers act, where can they react on, what can they change. Of course, in the machine learning exercise, we also had a couple of lessons learned. We had to deal with shadow and different illumination with objects, false objects. So we now have, we built up a training base from 7 countries in Asia and Europe and extended that and had some quality checks introduced, but it's still, it's really an important thing to kind of look at the training data sets and also to retrain it. For example, if we have a situation like COVID with face masks suddenly in objects which we have not seen before. Just an example how this looks like. We get an image from a high altitude, then going down, having a lower altitude image, which is the left-hand side. We do the classification and then we can provide statistics, and statistics really is what is needed so that policies can be changed and actions can be taken. And we do that currently in Indonesia, but did that also in the Philippines, Vietnam, and Cambodia. Which brings me to the final part. we transferred this classification scheme recently on a camera system which is equipped on a cleanup vessel. This vessel, the upper left picture, is from Cambodia, where the NGO Everwave is currently operating this vessel from the company Berkey and collecting waste and litter from the rivers. And together with our camera system, which is looking at the conveyor belt and which is then used for classification tasks, so that we know what is on the boat, we know something about the recycling value, and we can already inform the recycling chain following up so that it can be more efficient towards the circular economy. And just a few days ago, we were granted a new project funded by German Ministry of Environment. And here we go back to our roots and we implement the classification and hotspot detection, both driven by AI algorithms on maritime pollution aircraft. So maritime pollution aircraft are out at the sea, they look for oil spills, but there is a new threat out in the environment, and this threat is litter. And so providing this technology, we hope that marine pollution control in the future will not only look for oil spills or large vessels, but they can also provide valuable input and information on litter spots which can be combated. It's a two-step approach of edge AI, fast edge AI, and then more intense CNN classification. But there's more to come up. Project just started 7 days ago. But it's fun to see that at this point that while I started my professional career after the PhD with being responsible for aircraft installations and sensors and operating them, it's interesting to see that things always return, and now I'm working on aircraft again. Of course, there are many more applications in ocean science where AI is of help, and I didn't touch the whole robotics topic here, and we will hear about in an upcoming talk about coral reefs and classification. So there are many more applications, and it would be very welcome for the ocean science community if you can contribute. There are also, this tendency is that oceanography is more and more from the desk and not out in the sea. Also, that's very interesting with all the automatic platform. And this needs a lot of AI and machine learning solutions. Okay, this brings me to an end. I'd like to thank you for your interest, and I'd like to thank all my supporters and especially my team. And I'm very glad to be here. Thank you for having me.
Thank you so much for that fantastic talk. This is great. We will move right on to the next talk, but please post any questions that you have for Oliver's talk already in the chat. We're collecting them on our end. So with that, I want to pass on to Andrea.
Good afternoon to everybody who is joining us today. Thank you, Lynn and David, for inviting me to present to the Climate AI webinar series. And yes, Oliver, that was a great presentation. Thank you for the overview of the AI applications for the ocean. I'm going to talk a little bit more into the application of coral reef mapping. And I am very pleased to share about the Allen Core Atlas, a new tool for informed coral conservation. So my name is Andrea Rivera Sosa, and I work as a project and outreach manager for the Coral Reef Alliance. And I collaborate with a wonderful global partnership, which is led by the Arizona State University. So the Atlas builds in memory of the renowned coral reef scientist, Dr. Ruth Gates, and philanthropist Paul G. Allen, who was the co-founder of Microsoft. And they both envision using the latest technology and a partnership of hundreds of researchers to map the world's coral reefs. So our work stands on their shoulder. So I hope this presentation will increase the understanding of how the Atlas is made, with a particular focus on the bleaching monitoring tool. I will provide a quick example and show how the bleaching monitoring works, and share some of the ways that the Atlas has been applied to conservation planning efforts. So the mission of the Alenquer Atlas is to develop the first ever globally consistent benthic and geomorphic map, and also a dynamic monitoring system of the world's shallow coral reefs. So by using millions of satellite images, here on the top right, algorithms and semi-automated machine learning tools, along with a collaborative effort from the scientific community, it has supplied over a plethora of over 450 georeference data sets. And we have now been able to map 253,000 kilometers squares of shallow coral reefs. And now we have an accessible, free tool for all researchers, managers, and conservationists around the globe. So here is a schematic example of the Alenquer platform, and where you can see you can access different layers of the globally consistent coral reef habitats. They're shown here as the benthic habitat map and the geomorphic map. So the benthic map has about 6 classes, including the grouped coral and algae class, and this is mapped onto 10 meters. And we also have available the geomorphic map that condenses reef categories into 12 geomorphic classes down to 15 meters. So the scientific work explaining the details of the classification is called reef cover. It's a coral reef classification for global habitat mapping from remote sensing. So if you click here, when you go on the website, you'll find more synthesized information about these categories and also the paper. So these classifications are obtained from the Planet Dove satellites. Here you can see an incredible level of detail on the surrounding the island. And this high quality imagery is obtained from the planet's fleet of over 200 Dove satellites, which are circling the globe, collecting high resolution imagery of the Earth pretty much every day. They're always on, monitoring broad areas, and they have an impressive 3-meter resolution. So the Atlas also uses Landsat 8 and Sentinel-2 satellites to complement some of the mapping work. So to create the global maps, in particular the benthic layers and the geomorphic layers, the mapping team uses georeference field validation data to train a machine learning algorithm. And it's essentially teaching the program to recognize different characteristics which are associated with certain benthic classes. And then it's able to sort into those mapping classes in a semi-automated process for an entire region. And for the monitoring systems, the satellite imagery is analyzed and processed to obtain turbidity estimations and a potential bleaching processing Sentinel-2 images. And I will go into that a little more soon. So this is a visual summary of how the Atlas is made with some of our different partnering teams. At the top, we have Planet Inc., which collects the high resolution imagery that we talked about. Then we have Arizona State University, who process the satellite imagery to provide a clear view of the sea bottom down to 15 meters in depth. And they take out the surface reflectance, the waves, and other particles that essentially peel back the seawater, resulting in a high quality global imagery mosaic where we base the benthic and geomorphic layers of the Atlas. So the ASU team is also responsible for the bleaching and turbidity monitoring systems. So after this stage of image processing, then the School of Earth and Environmental Science from the University of Queensland Remote Sensing Center uses the field data collected by many survey teams and existing data sets, and it generates maps with object-based analysis and machine learning techniques to provide the two layers that we finally observe when we go into the Allen Core Atlas. So this field validation is a collaborative effort between University of Queensland and National Geographic, but also hundreds of researchers that have compiled benthic data from their own research purposes over the last years, and they have shared it with the Atlas, thus making this sourcing a true collaborative effort from the coral reef community. So here in the top left, we can see one way of collecting georeference field data. So a diver can, or a snorkel can swim along a transect using a GPS unit attached to the diver with a plumb bob attached to a camera, and it can create images of the benthos with the same 1 by 1 meter dimensions. However, other types of georeference benthic data can also be used for inform the mapping process. So the goal of this process is to use the field data inputs from the benthic classes and calibrate by training the algorithm, and then training it to classify, and then also to validate and assess the map's accuracy. And essentially, we are mapping from satellites to pixels. So that field data helps do that, starting with the planet imagery, zooming into the 3 to 5 minute resolution, using machine learning and the semi-automated process that I talked about. And then this assigns pixels to map classes of the different classes that we saw from the benthic map, and also the geomorphic map. So the Atlas also has a quarterly turbidity monitoring system. And what's unique about it is that the algorithm behind the data accounts for bottom reflectance. So it allows for a higher level of accuracy for the level of turbidity that is observed from the water column. So this is an example of a turbidity image, but this feature is only available from download into once you go to the platform. And it shows the highest level of turbidity per pixel per quarter at a 10 meter resolution. So now I'll go into the global dynamic bleaching monitoring system, which is also based on satellite detection, and it changes or it detects changes in the spectral signature of coral reefs, which flag potential bleaching events in near real time. As we all know and have seen in the past few months with what has been happening in the Great Barrier Reef, we've seen that many as marine heat waves increase, we are observing more frequent and massive bleaching events, and they're becoming more recurrent, and they're impacting large-scale reef areas. So the bleaching monitoring system helps process these satellite images when a region enters a NOAA bleaching alert due to the warming waters. And then what the Atlas does is that it measures the bottom reflectance or the brightness of coral reefs in these alerted areas in biweekly periods until the area has no stress. So it does this by defining a baseline color or a bottom reflectance of the reef area during periods of colder water, and then compares it to the brightness of areas during periods of warmer water. So as temperatures continue to rise, corals may become stressed and lose their symbiotic algae. And as heat stress continues, this can be observed as a change in the reflectance value. So the Atlas has 3 different bleaching categories, and they're based on the number of weeks that the brightening or the reflectance values have occurred. And they range from low moderate to severe. But I would like to show you quickly how that actually can be observed on the platform. Let me see if I can just do a quick change, and I'm going to stop sharing for a second and then share again. All right, it's not picking it up. So I'm going to go back to sharing the PowerPoint. Okay. So once you go to the Allen Core Atlas, you'll have this welcome picture, and then it's best for you to sign in so you can be able to have all the features of downloading the data. So then you can visualize the bleaching, and it will show you this pop-up, which just says that the bleaching detection system is it's under beta stage, so all the feedback that can be provided is very useful. So you press OK, and then to observe the bleaching, you can toggle to the right. Here you see a different panel where you can see bleaching, the benthic map, the geomorphic map, some of the labels, and then some other resources. I have already put on the satellite reef imagery that you can observe, and I have already toggled on the bleaching system, but you can't really see it because you have to zoom in. Since it's 10-meter resolution, you're not able to see it from when you have the screen zoomed out. So also, it's possible to toggle on the core reef watch information. So we talked about the bleaching alert areas being one of the cues to start the monitoring in certain areas. So you can select a date, usually matching the bleaching from the top, and then you can see the alert here. And we are zoomed into the Great Barrier Reef area. If we press on the legend, then we'll have the bleaching, which we can't really observe yet until you zoom in, and then the larger scale information from the NOAA. So if we further zoom into this area, let's say we want to go and see how this area has been affected. We have matched the dates, and then we can further zoom in, taking off the core reef watch, and then further zoom in, and then we can see that the legend shows that there's moderate bleaching in this area. So if we still further zoom in, we can see that the islands, the reefs surrounding these islands show that there's moderate, that there's low, bleaching in these areas for those dates. Something important here is to note that the bleaching layer is only applicable for the coral and algae class. So when we go back to the benthic map, we can select different classes. And here we see that the coral and algae class is the purple one, and then the bleaching layer is applicable just for this site. So if we want to look at other areas, we zoom out. And then, for example, here's another area in the center of the Great Barrier Reef where there's been reports that there's been bleaching as well. And here you can see how some areas show low to moderate bleaching. But it's important to note that the bleaching system is in its beta mode, and that all the observations help validate coral bleaching in different regions. So we need everybody's help to strengthen the tool that can benefit many reef managers worldwide. So there's different examples of data synthesis platforms that we're working with, for example, Cordio East Africa, and we're working together with Reef Check. It's another monitor organization worldwide. Reef Cloud also, it's a new platform which uses artificial intelligence to help analyze photo quadrats from the reef. And in addition, we are partnering with the Mermaid platform, which is an open source application that helps gather coral reef data worldwide. So all these platforms help validate the Allen Coral Atlas monitoring system. And just to finish off, I would like to talk about a few ways that the Atlas is being used at the global and regional scale. So some of these habitat maps are being used by NGOs, by governments to prioritize different environmental and economically sensitive areas, as well as habitats for key species. Also for post-cyclone disaster relief assessments, and for helping the coastal recovery in certain areas. The geomorphic maps, for example, are being used for aquaculture suitability sites and sea level analysis. Currently, the bleaching layer is helping validate some of these areas that are more sensitive to bleaching, and turbidity maps are helping monitor erosion in different locations in the world. Last but not least, the marine protected areas maps are being used to inform the 30 by 30 policy. And this is a new feature that was a highly requested feature to the Atlas, and it shows the marine protected areas found in the world database of marine protected areas, and it may play a huge role in remotely managing these coastal ecosystems, and also knowing how much of the economic exclusive zones are being protected through ecosystem-based management approaches. So if you want to hear more stories about how the different stakeholders are using the Atlas, you can visit the story map, or even better, contact us if you're wanting to share your story and how you're using the Atlas with your work. And if you're interested in further resources, we can highlight the Reef Resilience Network course. We also have other workshops and that you can see on our website. So please tell us your Atlas story so we can highlight how you and your team use the Atlas. And because our time is short, I would like to encourage you to connect with us either on our socials here. So thank you so much for listening. Please use the QR code for links to the resources that I mentioned, and stay in touch. Thank you.
Wow, thank you so much. Those were two really informative talks, and I really like that you gave so many pointers, both of you, to more resources at this intersection. We got a lot of questions in the chat, and we have a few minutes to talk about some of them. First of all, really quickly for Andrea, there were two questions on the work that you presented. One was, is the machine learning model using point-based or polygon-based approaches? I hope this makes sense to you. Otherwise, we can skip this or clarify in the chat. And the other question was, can red tide be seen in the monitoring methods?
So to answer your first question, I am not sure. I will get back to you, find your name, and send the answer to you. I am not exactly sure if it's point-based or polygon. But for the second question in regards to the red ties, we don't have a specific a specific layer for red tides, but the one that we have is for turbidity only. But there are some new features that are coming soon with other reef threats. So stay tuned for these new features. I do not know if red tides are in those features though.
Thanks. So then we got two questions that I'm going to lump together, and maybe both of you may want to weigh in on these. So the audience was wondering if you could share some challenges that you're facing with applying AI to marine science. And if you could also talk about like opportunities for data scientists who maybe are not working in academia to get into the field or help out with these endeavors. Maybe we can start with Oliver.
Okay, yeah, thank you. So one of the large challenges of oceanic research is temporal and spatial scales. I mean, we have processes from milliseconds and millimeters to basin scales, and we have only, even if we have thousands of robots out in the sea, we have big gaps in the data. So data quality and all the handling of the data and bringing it at similar grids, etc., comparable, getting rid of sensor drift and sensor biases is a major issue. So this is really what we are facing in the oceanographic community. But if we would have that, it would be much more easy to implement that information that we measure in the models. And that is, so it's sometimes it's not really finding the latest AI algorithm or machine learning algorithm which can do something very specific. It's more like it's a data-driven, I would see it as a data-driven side. What I'd like to see more is also multimodal information to fuse data. For example, also from, it was a bit in the, very nicely in the coral reef talk where you had satellite information, but also diver information, and in between vessel observations, something like that. Maybe also bringing in social media information that people take when they're out at the sea. So I'd like to see a bit more of merging different levels, and that would involve people stronger. Yeah, an entry point, Argo data. We have 4,000 robots in the sea, and they have a lot of data which is all freely available. If you want to start with a data set, look at Argo. I will post a link here to the website.
Thank you. Andrea, what's your take?
Yes, so and specifically for what I've talked about, there are many opportunities for people who work people who want to be involved in collecting coral bleaching data at the citizen science level. So there's different methods, for example, where people can take photos of the areas that they visit, and then for example, in the Philippines, they do this, and there's categories that they use for a landscape photo to know how much an area has been bleached. Because we know that scientists can't always be there doing more quantitative work. So qualitative information also is very important. And I think that's an opportunity for reef divers and people who work at dive shops, for example, or tourists. In Australia, for example, there's a Coral Reef Watch program where anybody can use a health card to monitor coral bleaching. So these are two examples of how citizen scientists are being involved, and that information is also helping us validate the tools with the observations on the ground.
Thank you so much. I may take the time to ask a question for myself, because you worked in very different, very specific, sensitive ecosystems. So Oliver, you work with the Wadden Sea, which is a very specific North Sea ecosystem, and I'm working on coral reefs that don't exist all around the world, right? So I was wondering how much of your work is really specific to a location, and how much of it can translate also to other settings and other ecosystems. And whoever wants to jump in.
I can start here. Well, the Wadden Sea might be a unique UNESCO World Heritage, but there are many barrier islands, many Wadden Seas, many coastal areas around the globe. I mean, you find them along the East Coast. You find a lot of the US. You find a lot of barrier islands, and you find a lot of these beach systems. I think there is about 300,000 kilometers of beaches on the high energy beaches along the globe. So there are a lot of these coastal systems which are comparable. And also, I mean, I showed this example of wind energy, and offshore wind is a major factor in many areas of the world for energy, getting energy out of the sea. So it is fully transferable, and also there is general learning in it. I mean, also with the LITER project, it's applicable to many areas. So I think it's not really restricted, but what we do best is in our area where we have the main knowledge. That is, of course, it's kind of our home garden.
Thanks, Andrea.
Yes, in our case, the Island Core Atlas is the first globally consistent mapping of the world's reefs. So it is applicable to the reefs worldwide. And we have been working with many different stakeholders and scientists all over the world to help validate those maps. We're actually in the second phase of remapping some areas to further strengthen the mapping products, because we know that since it's a global database for the maps, sometimes the very fine scale mapping in certain areas might not be so accurate. So we're working with those groups in different locations in the world.
Thank you so much. We're unfortunately out of time, but this has been really interesting. And Oliver already posted some more pointers in the chat. And I want to both thank you so much for joining. Both of our speakers have joined from very different parts of the world. Andrea called in from Mexico, Oliver called in from Germany. We are so happy to have you. Thank you for providing us with this talk. And thanks everybody for attending.
My pleasure.
My pleasure too. Thank you very much.
Thank you very much. It was a great opportunity.